In Activity 5, a compass in a circuit, students make a circuit and observe that electric current flowing through a wire deflects a compass needle. They first construct a circuit, then observe the interaction between electric current flowing in a circuit and a compass, and conclude that the flow of electric current in a circuit creates an electromagnetic field. You will need the following materials from the kit: Activity Sheet 5, Parts A and B, compasses, D-cell batteries, battery holders, electrical clips, rubberized magnets, 30 centimeter lengths of thread from Activity 1, wire cutters, roll of plastic insulated wire, and masking tape. You will also need to provide metric rulers and transparent tape. To prepare this activity, make a copy of Activity Sheet 5, Parts A and B for each student. For each team, cut 2 lengths of plastic insulated wire, one 15 centimeters long, the other 60 centimeters long. Strip about 1 centimeter of insulation off both ends of each wire. Each team of 2 will need a compass, a D-cell battery, a battery holder, 2 electrical clips, a rubberized magnet, 1 or 2 pieces of tape, a 30 and a 60 centimeter length of wire, and a 30 centimeter piece of thread. To begin the activity, distribute the compasses. Remind students how a compass behaves and that its needle is a magnet whose colored tip always points toward the south pole of a magnet. Then distribute Activity Sheet 5, Parts A and B, and the remaining materials. Ask students, how do you make a circuit? What is electric current? Students may know that a circuit consists of an energy source such as a battery and a path through which an electric current, a flow of electrons, can occur. If necessary, explain that electrons are tiny particles that orbit the nucleus of atoms and that carry negative electrical charge. Show the students how to place the battery and electrical clips in the battery holder and how to make a circuit by connecting the short piece of wire to the 2 clips. Tell students not to connect the wire until they are ready to conduct their experiments, as it will cause the energy stored in the battery to drain quickly. Instruct students to complete Steps 1 and 2 as described on Activity Sheet 5, Part A. Tape or tie one end of the thread to a magnet. Tape the other end of the thread to a surface so that the magnet swings free. Then, connect the short piece of wire to the electrical clips. Place the circuit so that the wire is vertical and close to the magnet. Instruct students to record their observations, then turn the circuit 180 degrees and record their observations again. Next, place the circuit so that the wire is horizontal. Then turn the circuit 180 degrees and record how these positions affect the magnet. Next, ask students, did you notice any interaction between the circuit and the magnet? Between the circuit and the compass? What happened to the compass when you moved the wire back and forth? Students should report that the circuit acted like a magnet in that it seemed to have an invisible magnetic field around it that was interacting with the magnetic fields of the magnet and the compass. The compass needle was deflected as the wire was moved closer and farther away from the compass. Then ask students, what can you infer about the relationship between the electric current in a circuit and magnetism? Help students understand that the electric current flowing through the wire creates a magnetic field around the wire. Explain that a magnetic field produced by a current flowing through a wire is called an electromagnetic field because it is produced by an electric current. Next, ask students, what happened to the magnet when you turned the circuit 180 degrees? They should see that the magnet turned in the opposite direction when the circuit was rotated. Explain that just as a magnet has a north and a south pole, so does the current-carrying wire of the circuit. The polarity, or north-south relationship, is determined by the direction of the current in the circuit. When students held the circuit so that the negative terminal of the battery was up, the wire had a certain polarity. When they then turned the circuit so that the positive terminal was up, the polarity of the wire was reversed. Following the instructions on Step 3, instruct students to disconnect the short piece of wire from the clips. Then, wrap the long piece of wire once around the compass so that it lines up with the compass needle. Next, connect one end of the wire to an electrical clip and touch the other end of the wire to the other clip. Tell the students to alternately disconnect and connect the wire and ask, what happened to the compass needle? students will see that the compass needle moves when the wire is connected to the battery. Help them understand that the needle is affected by the wire only when both ends of the wire are connected to the battery, because only at this time is current flowing through the circuit. Then, instruct students to make several wraps of the wire around the compass and repeat the procedure. Finally, ask students, what effect does the number of turns of wire have on the strength of the electromagnetic field? They should respond that when more turns of the wire are used, the compass needle is deflected faster and farther, indicating an increase in the strength of the electromagnetic field. To conclude the activity, remove the thread from the magnets and return them to the kit. Return the pieces of wire and the other equipment to the kit so that they may be used again. For science background, reinforcement activities, curriculum connections, and information about the Delta Science Reader, please consult your DSN Teacher's Guide.